In adversarial search, games are scenarios where two or more players make moves in turns with conflicting objectives. Each player aims to maximize their own chances of winning while minimizing their opponents'. Games like chess, tic-tac-toe, and Go are classic examples. The goal of the search algorithm is to find the best possible move for a player, considering possible counter moves by the opponent. In games, optimal decisions refer to the moves that lead to the best possible outcome for a player, given the current state of the game and the potential actions of the opponent. These decisions are determined by evaluating the game state and predicting future states based on possible moves by both players. Adversarial search algorithms, such as minimax with alpha-beta pruning, aim to find these optimal decisions by exploring the game tree and selecting the move that maximizes the player's chances of winning or achieving their objective. Alpha-beta pruning is a technique used in adversarial search algorithms, such as the minimax algorithm, to reduce the number of nodes evaluated in the search tree. It works by pruning branches of the tree that are guaranteed to be irrelevant to the final decision. Here's how it works. 1. During the search, the algorithm maintains two values, alpha and beta, representing the minimum score that the maximizing player is assured of and the maximum score that the minimizing player is assured of, respectively. 2. As the search progresses, the algorithm updates these values based on the explored branches of the game tree. 3. When a node is being evaluated, if it is determined that the node's value cannot affect the final decision, i.e., it is either worse than the current alpha or better than the current beta, the algorithm prunes the subtree rooted at that node, avoiding further exploration of those branches. 4. This pruning dramatically reduces the number of nodes that need to be evaluated, leading to faster and more efficient search. Overall, alpha-beta pruning helps to improve the performance of adversarial search algorithms by avoiding the evaluation of irrelevant parts of the game tree while still guaranteeing the same result as a full minimax search. Real-time decisions refer to the process of making choices or taking actions in response to changing circumstances or events as they occur. These decisions often need to be made quickly, without the luxury of extensive deliberation or analysis. The impact of real-time decisions can be significant, especially in domains such as finance, emergency response, and gaming. For example, 1. Finance, in trading and investment, real-time decisions can mean the difference between making a profit or incurring a loss. Traders need to react swiftly to market fluctuations and news events to capitalize on opportunities or mitigate risks. 2. Emergency response, first responders, such as firefighters and paramedics, must make split-second decisions during crisis to save lives and protect property. These decisions can impact the outcome of the emergency and the safety of both responders and victims. 3. Gaming, in video games, real-time decisions affect gameplay and determine success or failure. Players must make quick strategic choices, such as which moves to make or which weapons to use, to outmaneuver opponents and achieve their objectives. The impact of real-time decisions is influenced by various factors, including the accuracy of available information, the speed of decision-making processes, and the consequences of the decisions. Effective real-time decision-making often requires a combination of experience, intuition, and the ability to adapt to changing circumstances on the fly.